Hi. We're going to simulate casting dice and then figuring out how many different ways of each total result there are, and then drawing a diagram that shows the frequency for each one. So first, let's start by throwing the dice. And this is actually interesting because we can think of the dice throws as indices. So each die represents one independent dimension in the full set of possible outcomes. And so if we have 3 dice, then each one of them can contribute with a magnitude along that its own dimension. Which means that throwing dice is actually the same thing as creating indexation vectors. And if we want to make all the different possibilities, that's the same thing as creating an index, a table of contents of an array that has the dimensions of the number of sides in the dice. So for a normal die with 6 sides, then the iota function, which generates indices, does exactly what we want. So there are 6 possibilities, the numbers from 1 to 6. And if we have 2 dice with 6 sides each, then we can get this collection, which is a 6 by 6 array of 2-element vectors into the space, each vector representing an outcome. And then we can sum each one. So this is a plus reduction on each. And that gives us all the outcomes as a 2-dimensional array because there are 2 dice. And if we do this with more dice, then we get a whole lot of numbers like this, and it scrolls by. Let's try, instead of normal 6-sided dice, to have a 2-sided die that is a coin flip. A 3-sided die, that's a bit difficult to build, but it can be done as a kind of weird twisted piece of something that can land in 3 different ways. And then we can even do a 6-sided normal die there. So here we see the full space is a 2 by 3 by 6 array, and then we have summed all the numbers, and these are all the outcomes, which means we can ravel this, that is, remove the shape, we just get a flat list back, and that gives us this very long list of possible results. And since we start off with the lowest possible value, and then we increment by 1 going along the in ravel order, that means we already have our possible outcomes in sorted order. We'll never get a smaller value after we've gotten a larger value. Therefore, we can take this and throw it at the key operator. It's a higher order function that takes an operand, that is a function. In this case, we'll write it as a lambda. And it calls this function as many times as there are unique elements. So we will call it on 3, 4, 5, 6, 7, 8, and then eventually on 9, and so on, up to the top value, which is 11. And for each call, it will give a left argument represented by alpha and a right argument represented by omega, left and rightmost elements or letters in the Greek alphabet. The left is going to be the actual value, and the right is going to be the indices where that occurs. So we can see that we here have all the outcomes, and here the indices where this occurs. So 3 only occurs in the beginning, 4 appears in position 2 and position 7. So we can see the second 4 over here, and also position 19. That's the one over here. But we're not actually interested in the indices themselves. We just want 1 asterisk for each index. And we can write that by taking an asterisk and making it into a constant function and applying that to each index. And that gives us our possible outcomes for these three types of dice, and we can try this for two 6-sided dice. Then we get this, and for a single die, there's just one outcome for each possibility. However, this has an issue, and that is that we, in the process of computing like this, we have created an array of the number of dimensions of the count of the dice. And this is problematic because there is a limit in dialog APL to the number of dimensions you're allowed to have in an array, which is at 15. So if we have, say, 16 coin flips, so this is a reshape, so we're reshaping 2 into length 16, then we can see that the result array would have too many dimensions, and that's not allowed. So we need to solve this problem in a different way. So how can we do this? We can still think about it as indices into an array, but this kind of indexing is also a mixed based system, actually, or in this case, if they're all the same, this is the same base system. What does that mean? It means if we look again at this array, then we can see that it's like a number system where we're counting up. We start 111, 112, so this is the ones place, and this is the 6th place. We can see once we reach to the end here after the 6, so this corresponds to a digit 0, a digit 1, digit 2. So once we reach the digit 5, then there are no more digits in the ones place because it's the final base 6, and then we continue by incrementing the next number over. So this would correspond to the number 10 in base, the mixed base 236. So this looks a little bit funny because we start with index origin 1, but if we subtract 1, notice APL uses a high minus for negative numbers, then we can kind of see the numbers as they progress. So 0, 1, 2, 3, 4, 5, and then 1, 0, 1, 1, 1, 2, and so on. And over here, and we can then, by the time we get to 2, 5, then since the middle one only is base 3, the middle digit is only base 3, we need to progress to the top digit, which is not the 100th place, but rather the 3 times 6th place. That is the 18th place. And then we progress to that, and this is the last number before we need to add one more digit. Okay, so how many are there here? Remember how we did the sum reduction to get the addition reduction to get the sum? So too we can do multiplication reduction to get the product. So there are 36 possibilities when we have a specific ordering of the dice here, and we have to because they're all different here. And we can generate all these numbers. Again, we need to subtract 1. And now we just need to express them in this mixed base. So we can say 236 encodes, so a base looks like this, so this is evaluation in a base, and this kind of looks like a T, so it's converting to that base. So we're taking these normal decimal numbers and we're converting to the mixed base 236, and that gives us this one number per column. Notice that. So this is number 0, number 1, number 2, and so on, and then we get number 10 in base 236, and so on. And here we never exceeded rank 2. We are just dealing with low rank arrays. And it's also beneficial because we don't have this array of arrays, a multi-dimensional arrays of little vectors. We're keeping everything flat, and that's going to be much more performant. Now that we have this, we need to add 1 back again because dice, they start with 1, 2, 3 and instead of 0, 1, 2. And then we just need to sum vertically. So we're using the plus but this time we're using reduction with a bar on it, which means we're reducing vertically, actually along the leading first axis. It gives us all our outcomes. So this is the same thing that we had from before, with the reduction on each of the indices of an array that has the shape 2, 3, 6, where we then ravel them. So we can see that. This is the same, but this time without any issue, that if we try to use 16 coin flips, for example, that just works. No problems there. Okay, then we can go in and put in our function from before, where we use key, left argument, and an asterisk constant for each of the indices. And then we can see we get some huge thing for this very big conflict, but it works. And if we try to do this on our 2, 3, 6 case, we got the nice curve from before. If we try to do it on 2 dice, then oh, this what is the problem here? This doesn't quite look right. That's because we're using. We should go back again. Try this one. This coin flip here. We need 16 reshape 2 over here. There we go. That's better. Of course, if you have 16 coins and they both contribute 1 and 2, then the lowest value you can get is 1 for each one, so that's 16, and then going up from there. And then we can try our 6, 6 case. Have a 6, 6 over here. There is but one little problem, and that is if you only have a single number here, then expressing it as in the base here is going to just give us a flat vector, but we want to explicitly make this a vector rather than a scalar, which gives us a matrix, and it doesn't actually look different, but it will make a difference when we use the key part. So this is correct, whereas if we didn't do the ravel into a vector from a scalar, then we get a rank error. So that's important. There are different ways we can do this, but now let's make this whole thing into a proper function. We put braces around it, substitute an omega for the argument, and now we have a function that we can use and that doesn't hit any issues with the maximum rank. And it works as well on a scalar. Thank you for watching.